Discuss about ABAB stacking sequence. So in the previous video, we have seen that how the atoms are arranged layer by layer. So here in that video, I have mentioned that the various stacking sequence are ABAB and which will give you hexagonal close pack structure. And then you have ABC like that, which will give you a face-centered cubic structure. So these are the two important stacking sequences. Apart from this, you have stacking sequence like you have a different, you may have different stacking sequence like ACB like that. But the commonly seen stacking sequence, very commonly seen stacking sequences are ABC. So in this video, we will discuss about ABAB stacking sequence, or it can be better called hexagonal close pack structures. Close packed structure. Okay, we will see how it is. How we will see the structure of this solid. So in this video, in this picture, you can see here uh, the difference between two stacking sequence. The first one will lead to this AB stacking sequence, and second one is this ABC stacking sequence, which will give you the face-centered cubic structure. So see, it all depends upon where you are keeping the next layer of atoms, where you are keeping that void, either in B position or in C position. Okay, so if you stack this layer of atoms like this, the three-dimensional picture will look like this, and this will give you a hexagonal close pack structure. Right? We will look at a different picture here. Okay. See. So this is this AB stacking. So this one is A, this one is B, A, B, like that. It goes on like that. So if you want to select a basic building block, a basic unit cell here, which will be repeated to generate the entire uh, crystal, then you can select a hexagon on top of that. Okay, you can select a hexagon here. So this is, I have selected the hexagon here, uh, and you can see that this is this is the top layer. So this can be extended up to here, up to this layer, from this A layer to this A layer. Okay, so this is what shown here. So this is what is shown here. Okay, so on top you can see there is a middle atom here, and here you have an atom. See here we have shown only the lattice position. We are not assuming the atoms to be hard spheres which are touching each other. So you can see that this middle atom, this is touching this atom. Okay, these are in contact with each other. These are also in contact with each other. These are in contact with each other like that. Okay, I have shown only the position by these atoms here. Actually, these are touching with each other, and also this atom is touching with this atom, and this atom. Okay, and this atom is touching with this one, and this one. Okay, so this is how the structure of HCP structure is like. So here, first we want to find uh, the coordination number or kissing number. Okay, okay. So this is defined as the number of atoms that is in contact or that kisses with a particular atom. If you take an atom, what are the number of immediate atoms that are in contact that touches this atom? Okay, if you take that is called the coordination number or kissing number. So to find that, so let us take this particular atom. Okay, take this atom. Okay, this is the atom you will select. So this atom, you can see that this is in contact with this one, this one, this one, this one, this one, this one. So totally six atoms are in contact with each other. And also there is a layer just below that, that is the B layer. So it is in contact with this atom, and this atom. Similarly, it is contact. So a layer of atoms will be above this. Okay, a B layer is above. So that will be in contact with that layer of atoms. So three atoms in on top of this. They will also be in contact. Okay, so the total number of atoms is six, that is on side, plus three on the bottom, plus three on top, three on top. Okay, this will be 12. So the kissing number or coordination number is 12. So that means a particular atom. So this is applicable for any atom that you select. If you select an atom here, then that is also in contact with 12 other atoms. So it is easy to take this atom and find the immediate neighbors. So that's why I have selected the earlier atom. So the coordination number is 12. So coordination number is an important parameter that need to keep. That is, you need to find it in different crystal structures. For HCP structure, hexagonally closed pack structure, the coordination number is 12. Okay. Then, so the next step is, and then we will find here for a hexagonally closed pack structure, we will find the lattice parameters. The lattice parameters. So here the lattice parameters are, see, this one is A, and that is the side of the hexagon. We will take this as lattice parameter. And C, okay, C is the distance between the bottom A layer and the next A layer. So that is C. Okay, so, so lattice parameters are C and A. So C, you can see that it is the twice the interplanar spacing, twice interplanar spacing, and A is the length of side of hexagon, side of hexagon. Okay. And so next is, so if you take, see, this is an equilateral triangle. Okay, if you take, you can draw triangles like this. Okay, so this can be, you can draw triangles for a hexagon. So this is a hexagon. Okay, so this is the hexagon. So the here this is the side, and so you can draw six triangles here. So this triangle side is A, and this angle is 60 degree. Okay, this also we should keep in mind. And you can derive the ratio between C by A. But for in this video, I am not deriving C by A. It is actually equal to 1.633. We will use this value for calculating the packing efficiency. Okay. Next, what is the number of atoms in HCP unit cell? Okay, we have selected a unit cell that appears to be a shape of a hexagonal-like structure. So what is the number of atoms here? So in order to calculate the number of atoms, uh, you can see that. So these three atoms, if you take this unit cell, these three atoms will be there. Okay, And these atoms, you can see that this is shared between two units. And this atom is also shared between two units. And these atoms, okay, these are shared by six units. Okay, these atoms are shared by six units. So that means uh, there are three atoms which are not shared at all, plus two atoms which are shared by two units. So 2 into half plus 3 plus 2 into half. Then you have 12 atoms which are shared by 6 units cell. So 12 into 1 by 6, that is equal to 4 and 6. So there are totally 6 atoms in a HCP structure. Now, so next we need to find out the packing efficiency. Okay. Packing efficiency is defined as uh, this is equal to volume of atoms in HCP structure divided by the total volume. Divided by the total volume. So then you need to understand what is the volume of one atom. The volume of one atom is given by, we are assuming the atom to be hard sphere. So it is 4 by 3 pi r cube. Okay, 4 by 3 pi r cube. So and then so there are totally 6 atoms here. And what is the total volume in a HCP unit cell? So total volume can be found out by area of this hexagon into its height, that is C. So this is equal to, for an area of hexagon you can find by, I told you there are 6 triangles here, that is 1, 2, 3, 4, 5, and 6. So there are 6 equilateral triangles. So this is equal to 6 into root 3 by 4 into a square into C. So this is the volume of the hexagon. Uh, so volume occupied by atoms is equal to 6 into 4 by 3 pi r cube. Okay. But we don't know the relationship between R and A. So to find that, so you can take any one layer here, okay, for this hexagon. Okay. See, if you take a hexagon structure here, you can see that this is A. So this side is A, and so this A can be written as 2 into R because these two atoms are in contact with each other. I am connecting with the center of this atom and center of this atom. You look at this one. This is A, okay, and this is R, and this is R. Okay, half of this atom. So A is equal to 2R. That is the relationship we will use. So relationship between A and R is A is equal to 2R. So that means A is equal to 2R. Okay, see. So now you can find the packing efficiency. So packing efficiency, that is PE, is given by 6 into root 3 by 4a square into C divided by uh, sorry, okay, volume of atoms is equal to 6 into 4 by 3 pi r cube divided by 6 into root 3 by 4 into a square into C. Okay, and we know that this A is equal to 2R, so you can use that expression. So this is equal to 6 into 4 by 3 into pi r cube divided by 6 into root 3 by 4 into, so this a square can be written as 2r the whole square into c. So, and we have already seen that c is equal to 1.633a. Okay, so this is equal to 6 will be cancelled off. Uh, so this is equal to 16 divided by 3 root 3 into pi into r cube divided by 4 into r square into c. C can be written as it is 1.633 into a. This a is equal to uh, 2r. Okay, so this 1.633 into 2r. So you can write this as, so this will be cancelled of 4, and it is 4 4 pi r cube by 3 root 3 into r square, so into r cube into 2 into 1.633. So this will be cancelled off. This is 2. So if you solve this, you will get 0.74 or 74 percentage. So this is the packing efficiency of hexagonal close pack structure. Okay. So far we have discussed about the type of stacking sequence in a hexagonal close pack structure. So we have seen that it is AB, AB, AB stacking sequence. If you have ABC, ABC, ABC sequence, we will get a face-centered cubic structure, which we will discuss later. And this can be, so unit cell we are selecting here is a hexagonal like structure, hexagonal close pack structure. You can see that. So first we will find the number of atoms that is in a unit cell. So that is equal to number of atoms is 6. And then we have found the coordination number of kissing number, that is number of atoms that is in contact with a particular atom. So for easiness, we have selected the atom at the middle. So this middle atom is in contact with 3 atoms on top and 3 atoms on bottom. And on the side, it is contact within 6 atoms. So totally 12, it is directly in contact with the 12 atoms. And here the lattice parameters are A and C. Here, A is the side of the hexagon and C is the distance between A layer and another A layer on top. And the ratio between C by A, this is, can be derived, but here we are directly writing it as 1.633. So number of atoms in unit cell is 6 atoms. So the packing efficiency is volume of atoms in HCP by total volume. So you will find the packing efficiency as 74%.